Every query your RAG system handles runs the full pipeline, embedding the question, searching the vector database, calling the language model, running the hallucination guard. Each of those steps costs time and money. If 100 users ask essentially the same question across the day, you are paying for the same computation 100 times. Semantic hashing stores the answer to a question and reuses it for any future question. That means the same thing. Traditional caches match on exact strings. If a user asks what is the refund policy and the cache has an entry for that exact phrase, it returns immediately. But if the next user asks, how do I get a refund? The exact match fails and the full pipeline runs again. These two questions mean the same thing and deserve the same answer. A semantic cache embeds both questions, finds that they are very close in vector space, and returns the cached answer for the second query. The semantic cache sits in front of the full pipeline. When a query arrives, we embed it and search a small in-memory index of previously seen query embeddings. If the closest stored query has a cosine similarity above our threshold, we call it a cache hit and return the stored answer immediately. No vector database search, no language model call, no hallucination check. If nothing in the cache is close enough, we run the full pipeline and store the new query embedding alongside the answer for future use. We define a simple cache entry data class. Each entry stores the embedding vector of the original query, the answer that was generated for it, and a timestamp so we can expire old entries. We use a Python data class for clean field definitions and automatic defaults. The created at field uses UTC time, so expiry logic works correctly regardless of the server time zone. The semantic cache class stores a list of cache entries, a similarity threshold, and a time to live duration. The threshold of 0.92 is deliberately high. We only want cache hits when the questions are genuinely asking the same thing. A lower threshold risks returning the wrong cached answer for a superficially similar but meaningfully different question. The private embed method calls the same OpenAI embedding model we have used throughout the series. The get method embeds the incoming query and loops through stored entries. For each entry, it first checks whether the entry has expired by comparing the current time to the created at timestamp. Expired entries are skipped silently. For valid entries, it computes cosine similarity between the query embedding and the stored embedding. The first entry that meets or exceeds our threshold is returned immediately. If no entry qualifies, the method returns none, which the caller treats as a cache miss. The set method is simple. It embeds the query and appends a new cache entry. The created at timestamp is set automatically by the data class default factory. Note that we only call set after the full pipeline has run and the answer has passed the hallucination guard. We never store an answer that the system could not verify, because a cached hallucination would be served to every future user who asks a similar question. The final cached ask function is the cleanest wrapper we have written in this series. Check the cache first. If we get a hit, log it, and return immediately. If not, call the safe ask function from episode 10, which runs the full verified pipeline. After getting a clean answer, store it in the cache for next time. The second call with how do I get a refund returns instantly from cache because its embedding is close enough to the first query to exceed our threshold. A few production tips before we finish. Keep your similarity threshold above 0.9 to avoid wrong cache hits. A match at 0.85 might feel similar but could be a meaningfully different question. Set your time to live based on how frequently your source documents change. If documents update daily, set it to 12 hours. Persist the cache to disk or Redis so it survives server restarts. And always log your cache hit rate. Above 30% is where caching starts making a meaningful difference to cost and latency. You now have a semantic cache that sits in front of the full pipeline, returns answers instantly for similar questions, respects the time to live so stale answers expire, and never stores a hallucinated response. In the next episode, we cover fine-tuning embedding models on domain-specific data. When the general-purpose OpenAI embedding model does not understand your industry vocabulary, fine-tuning closes that gap dramatically. Subscribe so you do not miss it. See you in the next one.